Okay, for this video, we'll be constructing ozone, the Lewis structure for it. And before we start making our Lewis structure, we should figure out how many bonds this molecule actually contains. And we do that by using this equation right here. The number of bonds equals the demand minus the supply all over 2. So, what is our demand? Our demand is to satisfy each atom, we have 3 oxygen, to have a full outer shell or a noble gas configuration. We know oxygen has the octet rule, so it should have 8. So 8 times 3 is 24. So 24 is our demand minus our supply. Our supply is how many valence electrons each atom can actually contribute to the molecule. And oxygen is found in group 16, so it can each contribute 6. I say each because we have 3 oxygen, so 6 times 3 is 18. 24 minus 18 is 6. 6 divided by 2 is 3. So this molecule should have 3 bonds. Now what I have down here is our atoms already laid out. Between them are double-sided arrows all enclosed in brackets. This just means they are resonant structures. But let's construct one Lewis structure first, and then we'll convert that into the other resonant structure. And it'll make more sense when I actually do it. So a good idea is to connect all of our atoms first by single bonds. So what we have here is 1, 2 bonds. We can give 3, so 3 minus 2 is 1. So we have one more bond to give. We can place this bond between these oxygen or these oxygen. Let's just put it between these oxygen first. Now what we need to do is fill in our lone pairs. So this needs a double bond. Not a double bond. This needs 2 lone pairs. The middle one needs a lone pair. And the final oxygen needs 2 lone pairs. So what we have here is 2, 4, 6, 8, 10, 12, 14, 16, 18 total electrons, and that equals our supply, so we're good. So what we need to do now is the formal charge. So formal charge equals valence electrons minus our lone electrons plus the number of bonds. Now, let's look at this first oxygen first on the far left. So we have 6 valence electrons for oxygen minus our lone electrons, which is 1, 2, 3, 4, 5, 6 lone electrons on that atom, plus the number of bonds. Well, we form a single bond, so that counts as 1. So 6 minus 7 equals a negative 1. So this far left oxygen has a negative formal charge. Let's look at the middle oxygen. Once again, 6 valence electrons for oxygen minus our lone electrons. We have 2 on the middle oxygen. Plus the number of bonds. We have a single and a double. A double counts as 2, so 1 plus 2 is 3. And that will be 6 minus 5, which equals a positive 1. So let's do that. Now we could simply say that last oxygen is neutral because the negative and the positive will counteract each other and cancel out, and our molecule is neutral, so it should be 0, no formal charge. But I'll still do it. Once again, 6 valence electrons for oxygen minus our lone electrons, which is 1, 2, 3, 4, plus the number of bonds, which is 1, 2, or just a double, 6 minus 6, and that equals 0. So that is what our structure should look like. Now, when we construct our resonance structure, we're going to use the method called electron pushing, and we do that by going from the side with the negative formal charge towards the positive. And now what we can do here is either move lone pairs to create bonds or break bonds to create lone pairs. So I'll show you what that means. But first, I'm going to reconstruct this molecule over here so it doesn't get really confusing. Okay, now that is done. We have just reconstructed our molecule over here. What we're going to do first is move a lone pair. So we're going from negative to positive, so we're going to take this lone pair right here and make a double bond. And when we move lone pairs, we will also be moving this negative charge. So now this negative charge is on this oxygen. But to make this look neater, I'm going to draw a line right here to indicate a double bond. So we now have a double bond over here. This oxygen is now neutral. And what we can do next is break a bond. The reason why is because we have 2, 4, 6, 8, 10 electrons surrounding this oxygen, and we can't have that because it violates the octet rule. So we're going to break a bond. So we're going to break this bond and place those lone electrons over here. So I'm just going to remove that and put a lone pair in. So now we have a lone pair. And keep in mind, this negative is still moving, so now the negative is over here. And that is it for constructing our resonance structure over here. We could check the formal charges to see if I did everything right, but I know I did, so we don't have to do that. So how do we determine which one is the best structure? Well, what our structure actually looks like is what we call a resonance hybrid, and that is a combination of all of our resonance structures. So not one alone is exactly what is not exactly what the structure looks like. It has to be a combination of all. But to figure out which one's the best of these two, we use these rules right here. So who's the best? Octet is always the best. Octet will override all of these rules. So we can see here each atom has an octet, so we have to move to the next rule. Least separation of charges. Okay, we have a negative here and a positive here, a negative here and a positive here. Well, we both have charges on each molecule, so next rule. Negative formal charge on most electronegative atom. Well, we have a negative on the oxygen and a negative on the oxygen, and they're identical molecules. So what we can say here is these are equally contributing to the resonance hybrid. So they are equally contributing, I guess you could say. So either one is your best structure. So that would do it for this video. I hope that it helped.